Very good. Then I'm happy to introduce today's speaker, Filip Strakoš, who will tell us about the index bundles and frame bordism. So take it away, Philip. Or I should say, as always, feel free to ask questions as we go, either in the chat or out loud. And there will also be an opportunity to ask questions at the very end after we stop the recording. So with that out of the way, go ahead, Philip.
Okay, thank you very much for giving me the opportunity to speak here. It's pretty fun and I'm learning a lot of stuff here. So heads up to the organizers who are administering this. It's a great thing that they are doing this. So what is my talk going to be actually about? I was asked to somehow try to explain to you this paper of Noah Porcelli, which uses some homotopy theory to orient some moduli spaces of some solutions over these extraordinary homological theories. What my talk is not going to be about is framed bordism, because it's somehow going to be implicitly there, but I'm not going to really cover that one simply because I was not really asked to. And yeah, I've learned this yesterday, that there is a frame bordism in my title of the talk. Anyways, let's start. So first, let me start with like philosophical remark. So why do we geometers care about this Floer homotopy theory? That we are expected to use this new technology to deal with situations which are somehow naturally coming in families that are somehow fibered. And today we will see an example of such a very, very old and classical situation where our Lagrangians or our situation is simply fibered. Why? Why should we care about Floer homotopy theory? Because those somehow situations, they induce moduli spaces of solutions, and the moduli spaces of solutions have bigger dimension than 0. We geometers usually care just about 0 or one-dimensional moduli spaces, but in these situations that is not enough, and somehow moduli spaces of arbitrary dimensions come into play. So yeah, that's why. So what is the plan of today? So this is incomplete plan because the slides are not yet done, but more than 1.5 of a talk is gonna go as follows. So first I will give you an idea about what I will not cover and what you will not learn from this talk, because at the end we will hear about these flow categories and this huge, beautiful new technology which is going to appear. And to be able to orient flow categories, we will need some notion of coherency. And I'm not going to talk about that today. So that is going to be the first part. Then I will tell you why I should care, because for me, there is always first the problem, and then there is the technical machinery to solve the problem. So I kind of feel when I'm giving a talk to first start with the technical machinery is wrong, because at the dawn of every geometric problem, there is a moduli space. So I will start with the things that we know, and then I will explain you how to tackle those moduli spaces. So that's going to be the geometric situation. Then I will somehow tell you what's the strategy of attack, how to solve this problem in a very cartoony and imprecise way, and which contains like a lot of analysis, but I'm going to skim over it, because if I try to explain it to you, I would have to go too fast for the homotopy people, and I would be too boring for the analytical people. So let me just sweep that under the rug. Then I will go into the weeds and somehow motivate for some of you why we geometers care about spectra, which are suspension spectra, and why for us stabilization is very natural thing to do. And then there are points which are not really there, and that is Cauchy-Riemann operators. And after that, I'm going to talk about Maslov index, about R orientations, and at the end, I will somehow talk about some special cases where this orientation business works. Okay, so let me proceed with the things that we are not going to cover today. So what we are going to cover today, we will have some moduli space, which maybe has some corner structure in it, and we will take some one-dimensional, like some path in this moduli space. This moduli space is gonna be a lot of dimensional. And what we are gonna do, we are gonna slowly approach this, slowly. We are going to approach this corner, but we are not gonna really get to the corner. We will stop at some point before the corner. And this point where we will stop is going to be chosen super carefully so that this path will create as a cobordism that we will somehow orient over some ring spectra so that it restricts well on the endpoints of the cobordism. So what we will not need is any gluing today, actually not even Gromov compactness. We will not describe corner structure, and I will not tell you how to choose these orientations coherently, which is precisely what has to be done if you want to orient the flow category. So let me I think that we kind of should have this in mind because we care about flow categories here. So how the orientation business works, this coherent orientation business works for Morse homology or for Floer theory in general. So I will do it only for Z orientations so that you have an idea. So how to do that? So we have to have a good control over the corner structure of our moduli space. So in here, you can see a moduli space, and we somehow have a corner there where the moduli space breaks down and it's no longer a smooth manifold, but it is somehow almost smooth with a corner. So there we need to good control over what that corner is. What we are going to get are Fredholm operators with index bundles, and we are going to take those index bundles and create somehow determinant bundles. Like if you don't know what those things are, just feel free to ignore me. And then somehow that's the orientation on this like big codimension 1 strata restricts well to the other codimension 1 stratas is just gonna get translated to some operations on those determinant bundles. So that's how the vibe is for Z orientations. And I'm asking, or you can ask, how to somehow follow a similar path, but much more technically challenging for Tom spectra. So you've learned from Trygve the last time what is a Tom spectra, hopefully what is an orientation and things like that. I will maybe recall what is an orientation, but you need a Tom spectra for that. And you somehow take a Tom spectra of some virtual bundle, and there you somehow clutch along like these two small strata along this corner, and you somehow have to relate it to this orientation here in the middle, and you have to all do this over like parametrized spectra. So it's for this homotopy theoretical machinery, it's a fun problem to think about. So just note that like, you know, this might not work as I write here. It's just like my intuition how it would work, but I'm not a competent homotopy theorist, so don't listen to me. Okay, so but a thing that I'm more competent in is this geometric situation. So I don't know about Floer theoretic people, how they know these things. So about the homotopic people. So let me just skim through the basics. So we will take a compact symplectic manifold, which is an even dimension manifold with a 2 form, which is smooth, non-degenerate, and closed. And we will take a submanifold of this symplectic manifold that is so called Lagrangian submanifold. And we will take what does it mean to be Lagrangian? It means that if you somehow restrict the symplectic form along the Lagrangian, it's gonna vanish. Or equivalently, if you pull back the two form with the Lagrangian embedding, it's the pullback is going to be vanishing everywhere on the Lagrangian. So our Lagrangians are going to be here compact, connected, and relatively exact. What does it mean? It's super important for this paper. And that means that if you have somehow something that lies in a relative pi2, which of your manifold, symplectic manifold M with a boundary of your Lagrangian, then the symplectic form somehow integrates to 0 on those on the representatives of those classes. So it's important for us to have some control over like symplectic volumes. Okay, so another important notion for today is the Hamiltonian flow. So what that is, it's a one-parametric family of diffeomorphisms of the symplectic manifold M that is generated in a following way. So there exists a Hamiltonian, which is like a one-parametric family of smooth functions on your symplectic manifold, parametrized by an interval. So that the flow, so the one parametric family of diffeomorphism is given by the solution of this ODE here that I wrote down. And what you can always somehow generically assume that the flow is somehow constant in the T when you are close to 0 or 1. Okay, so today, we will care about very nice Hamiltonian flows that preserve some Lagrangian that we choose setwise. So we are not going to preserve it pointwise. What does it mean? Like if you flow in time at time 0, it's an identity, this flow, but at time 1, it's something weird. But the point that you started with, it somehow can travel along the symplectic manifold, but it returns back to your Lagrangian L. Okay, so what you can do, it might not be the same point, you know, so it might be that this restriction of the flow acts as something which is not an identity on your Lagrangian, but we actually don't know how it acts on the Lagrangian. And that's the main question of today. When you restrict this flow 1 on your Lagrangian, it creates a self-diffeomorphism of the Lagrangian. And it's even a topological group, which is denoted by this beautiful curly G with a low script L. And you can somehow see from some very basic symplectic geometry arguments that this group is nothing else than somehow union of path components of the diffeomorphism group of L. So we somehow will study these path components of this group, you know. Okay, so this is not a like obscure question that no one would care about. This is a question a lot of people were asking. For example, Roux, Lalonde, and Leclerc, and they were able to prove the following interesting stuff. So they have shown that if you have Z2 coefficients, so you don't give a damn about any orientation, it actually acts an identity on the homology of the Lagrangian, right? But if L is relatively spin, then and this spin structure or this relative spin structure is preserved under the one-time flow. This one-time flow acts on as identity on the homology group with Z coefficients. Okay, so one sees that to somehow have some kind of orientation property, you have to have some restriction of on the class of Lagrangians that you are working with, and that is the way the life goes. It's a payoff. That you gain funny coefficients, but you have to restrict your class of Lagrangians. But what Porcelli has shown this public or uploaded to the archive this January is the following theorem. So there is an assumption that I call an assumption elephant, and because it's going to be the big elephant in the room for the rest of this talk. And that is that we will assume that some virtual vector bundle, which looks like that, it's just some index bundle minus some pullback of some projection. It's actually like it's actually a stable normal bundle is in some cobordism of one of the ends. And we will assume that it is R orientable, where R during this talk is going to be a ring spectrum, some ring spectrum. So if this assumption elephant holds, then you can say that this one-time flow, it actually is homotopic to the identity as a map of R spectra. And yeah, of those two beautiful spectra. So you take a suspension of L, you smash it with R to get this ring, this R module structure on it, and it acts there as an identity. So it's like the ultimate generalization of making your coefficients crazier and crazier along the way. So at the end of the talk, I will tell you, maybe, hopefully, what for like in which situation this elephant assumption is satisfied. So somehow naturally, when your ring spectrum is the Eilenberg-MacLane spectrum of the Z2, it works. If it's and you don't have to restrict your class of Lagrangians at all. However, if you choose Eilenberg-MacLane spectrum of Z, then you have to put some condition on the second Tethel-Whitney class of some two torus living in your Lagrangian and somehow extending to the symplectic manifold. So somehow the two torus is somehow fillable inside of the symplectic manifold. So that is a restriction. Or this complex-oriented K-theory that's...
sorry, I probably missed it, but it's a virtual vector bundle on what? On which manifold? On what is?
Sorry, I didn't hear you properly. Can you repeat your question,
I
please?
probably missed it, but it's a virtual vector bundle on what?
Yeah, that's a good question, and I will give you the manifold in a few slides. It's what it is gonna be. It is going to be a cobordism from your Lagrangian L to some other smooth and dimensional manifold, but that smooth and dimensional manifold, it is going to be called P, and it is going to have some natural projection to L. And this pi star TL is just like pullback of the tangent bundle of L with respect of this projection, and this virtual vector bundle is going to be like stable normal bundle in the cobordism. But hang on just for us a little more, and I will tell you what it is going to be, like what is the base of this bundle. Okay. Okay, where was I? Yeah, complex-oriented theory. So there you need to assume that L is spin or relatively spin. Then you have these all other theories, and there is a price to pay somehow making your class of Lagrangians smaller. Okay, so let me get to the construction of the base of the virtual bundle. So as I said before, in this geometry business, there is first a problem, then there is some genius comes to the problem and devises a partial differential equation and a moduli which creates you moduli spaces of solutions, and then you do stuff with it. So what are the moduli spaces that we are gonna talk about today? So you take some convex domain in complex numbers. You can imagine this picture on the right hand side, this G, but let's call it first C, so that it has 0 on its boundary, and it is located here in this upper half plane. Okay, so what more? You will have a function, a continuous function from its boundary to the interval so that it maps 0 to 0. Okay, so that's some domain. And what are going to be our maps? So we will care about the space of maps, which are going to be smooth maps from this domain C to our symplectic manifold M, so that for every point on the boundary, the corresponding point is going to get mapped to the flow out of your Lagrangian of the appropriate time. This looks horrible, but in here there is a cartoon example of such map. So imagine that your symplectic manifold is just S2, and that your Lagrangian is a circle, and your Hamiltonian diffeomorphism is just a rotation along the axis. So it somehow rotates this circle around the equator. And your disk is this purple thing on the top. I hope none of you is colorblind, which has boundary on these Lagrangians, and in a time t it moves, right? And this appropriate point is, gets mapped to the appropriate time of the flow out, where this is the time 0. Okay, so I hope that this helped as a cartoon of maps that we care about. And what can we say about such moduli spaces of maps? So there is a very natural projection, and that is you take such a disk or such a map of a disk, and you ask what is the point on my Lagrangian where this disk somehow evaluates, where I can evaluate the disk at 0. So that's the natural projection, and that's the first please keep this pi in mind. This pi in this whole entire talk means this thing. So the letter pi now is fixed. And okay, so that is some projection of some moduli spaces, but it turns out that those moduli spaces are humongous, too big, too many information. There is no order. So we will cut out of this moduli space a smaller moduli space, which is going to be fantastic. So how are we going to do it? We are going to choose some almost complex structure on my manifold M. If you have this example, you can imagine M being a Riemann surface. And on the Riemann surface, you everywhere have this actually an integrable complex structure. But we don't, in symplectic geometry, in principle, we don't assume that our almost complex structures are integrable. Oh my gosh, the time flies. So we are solving the following PDE, which is the Cauchy-Riemann equation. In a local conformal coordinates, you can write it as this. This almost complex structure is not integrable, so this PDE is nonlinear. And we are going to create some cobordism of solutions, and that we are going to do by considering different domains. So imagine this domain that you started with, you somehow cut it in half into positive, negative part, and you glue in between of them some long strip that looks like this. So this is like people who know this stuff, they could be confused and they would be okay, but this is unstable in the Teichmüller space, yada, yada, yada. But it is not, because we have this function on the boundary that we fixed. And so the boundary is parameterized, and you have no automorphisms. So this is a stable thing. And the functions on the boundary look like this on those boundaries. And Hafer in 88 has proven this statement, which is super important. So as you are gluing in these longer and longer strips in the target, these 2 points are going like they go closer and closer and closer to each other. But he never got to the end of this of this moduli space. So we are somehow going to insert longer and longer strips, and our our disks are going to be squashed more and more and more, but they will never like kind of this. They will never look like the red configuration here. Okay, so what is the cartoon overview of the proof of the theorem? So as we make the L bigger and bigger and bigger, this space of the solution of this PDE might be super nasty. So we analytic people, what we do, we say, okay, we are gonna save you, and we will say that if you vary also the almost complex structure, it's actually gonna be a smooth manifold. But there is this price to pay, and that's varying the almost complex structure. But what you can do, you can define this moduli space, which is just like you just collect all your moduli spaces you had along the way to one moduli space, and you parameterize it over the line like this. So there you have a natural projection, which I'm going to call P here. And at the start, you have this moduli space, which is called UF0, C0, J0. And at the end, there is going to be some other moduli space P. So what happens in reality as you start doing the computations, hell can happen, and you might have this cobordism is ugly. It has components of different dimensions, of non-constant solutions, very complicated structure. But as you increase your C big enough so that this guy is almost pinched, it looks really nice, and you actually get a manifold P, which is nice. So let me say this more properly. So you can buy some form of Gromov compactness, but you don't need the whole package. You can prove that the every of those slices is compact metric space. You can prove using standard methods in symplectic geometry that the moduli space that you start with consists only of constant maps. And that's precisely the point where we use that our Lagrangian is relatively exact. And so the projection pi, the evaluation map, is a diffeomorphism. So that's important. What is this this other projection? So it spits out this L. And when C is big enough and you choose C prime so that it's a regular value of this projection, you think about the path component of this moduli space that you started with, you get you get a smooth and plus one dimensional manifold, and your manifold P is the intersection of this component, with this pre-image of of your regular value p. C prime. Okay, so there is a different projection, and you can project not only on 0, but you can also project on I. And Heffer showed that that if C is huge, this UI is arbitrarily close to U0. So what it actually means, it means that you somehow this middle part of your disk is a constant map. And there you also need a relative exactness of your Lagrangian. And what you can write down is a projection. And it's a funny thing. These two projections are actually homotopic, this pi prime and pi. And the homotopy can be written out explicitly. And it looks like this. You just somehow flow back along this path in your domain. Okay, so this is yeah.
I'm confused. Isn't pi like pi is not from P, right? It's like from the whole. Like,
yeah, but you can
you just
have
restrict,
pi.
you just restrict.
Yeah, it's just
sorry.
restriction to P.
Sorry.
But it is a good question. Of course, the pi is a restriction to P. Yeah. So, okay, this was some analysis and some geometry, but what you should know as homotopy people. So we have these smooth manifolds. I write a superscript their dimensions, where W is a cobordism of some L and some P, so that these things commute strictly. And you know, moreover, that this thing commutes up to homotopy, where, you know, this is the homotopy thingy. Okay? Yeah, if you would like substitute here, I think pi for pi prime, you would get a strict strict commutative diagram. Okay, so these two diagrams are the thing that we will care about now, because we are homotopy theorists now. So what are the ideas? So our input is this diagram, and L is a nice Lagrangian, and it's nice enough so that the elephant in the room is fine. We will construct a stable normal bundle of P in this cobordism. So it is a normal bundle, like it is not really a normal bundle, it is a stable normal bundle of P. And it is equal to this virtual vector bundle. And this condition of L being nice and elephant being fine, this virtual vector bundle is going to be R orientable, and then there is going to be this machinery of homotopy theory where you're going to do Pontryagin-Thom for virtual bundles and crazy stuff, and that's gonna give you that this map here, where this curly P is this end of this cobordism, admits a section of R module maps up to homotopy of R module maps. So there is just gonna be, that just means that there is S going the other way, so that this is homotopic. This is a homotopy of R module maps. Okay, so what if you somehow look at the main theorem? What was it saying? So it said that if the elephant in the room is fine, then this map is homotopic to the identity as R module maps. And what is the proof? We can actually module all the details. We can kind of prove it. So you start with your flow time at time 1. You know that this fella is homotopic to the identity, right? So you just plug in the identity and you know that this is homotopic as R module maps, these two fellas. That's amazing. Then I remember this other diagram that we had on the previous slide. So that tells me, okay, if I have psi1 and pi, I can kill it and have just pi there. So we have this one. But now we again use this section here, and we get the homotopy as R module maps, and that's the proof. So the hardest part, I don't know. what is the hardest part. It probably depends on what is your background. For me, the hardest part was understanding the homotopy theory. For the homotopy theory, people is going to be difficult the first part of the construction. But somehow, if I should relate it to the motivations of these results, what are the, if I take the homology theory represented by the ring spectrum, so this result gives us that the time one flow acts as identity on the generalized homologies of our Lagrangian L, and it is not hard to prove it even for me. So if you take this generalized homology theory, it is defined like this. You take fundamental groups of this spectrum, and that is defined like mapping out of the suspension of the sphere spectrum. But there is a result that tells you that this is a complete same thing. So this is just like a homotopy classes of maps of spectra, but not R modules. But there is a natural equivalence that says that this is the same thing as mapping here, right? But in here, you know that this time flow one map acts as identity on those fellas here. So then when you're gonna do the, I don't know, like this map that is induced in this generalized homology theory, it's gonna be the identity. Okay, to scheme, yes.
So I might take you back, so feel free to say that. Like, I don't understand what is the map pi here from like suspension to infinity of p tensor r to suspension to infinity p tensor r. Smash before.
What is this? Is not map pi I. That's the I.
Oh, not here. Upstairs. Like the map that you claim to admit a section.
Ah, yeah, this one.
It's like, yeah. What is the pi? Where does it come from?
Yeah. So that is a map that is induced by this Pontryagin Tom construction. So like this Pontryagin Tom construction, it eats this original pi and spits out some. Okay, no, wait. Let me. Yeah. Yeah, there is not a short way how to explain it. Like in here, there is in between those two ends of this Pontryagin Tom line, there is a lot of pages of text, and I am not competent enough in homotopy theory to tell you a sleek way how to do it. Let's chat about this later, maybe. Sorry, but this pi is induced from this pi here in some way. Yeah, I'm sorry. This is not a good answer.
No worries.
But...
It's okay. Good talk.
Yeah.
I'm sorry.
Yeah. Let's chat about this later. Okay, for this cohomology theory, you can prove the same thing using some standard dualities for spectra. Just for not homotopy theory people, there is a typo in the paper on page 11. Like Noah missed this check in the statement, and that took me a whole afternoon to realize that that is wrong. Or like I thought that it is wrong, but I thought that I am not understanding it. So just be careful about it. It's like a small typo, right? But yeah. Anyways, so this is the main structure of the proof, and now I'm going to tell you somehow the main lesson for like even the further advancements of the theory is actually not this end of the construction, but is somehow this middle. So that's somehow the main lesson you should learn from this talk, is like how one constructs these virtual vector bundles here. And we are gonna do it now. So there is this, so let me give you like a short, because I don't know what you know about Fredholm operators, just a funny thing, Fredholm got a PhD here in Uppsala 126 years ago, so I should know this stuff. Okay, so what is a Fredholm operator? So we have two Banach spaces, a bounded linear operator in between them, and a Fredholm operator has a finite dimensional kernel, closed range, and finite dimensional co-kernel, which is that factor space there. You can define its index, which is a difference of those two dimensions. And examples of Fredholm maps are linear maps in between finite dimensional vector spaces over R or C, Cauchy-Riemann operators that we are going to talk about later, and Fredholm, which are also elliptic, which is going to be important at some point, and all the nice geometric operators are nice and Fredholm. Okay, so now we will do everything parameterized. So we will pick X being a nice base, for example, finite CW complex and a fiber bundle, where this fiber bundle are going to be some like Banach spaces pairs. And we are going to construct another fiber bundle, but actually with convex fibers, so that somehow it's going to have contractible fibers, and those are going to be spaces of some special Fredholm operators in between those two Banach spaces. And we will, because our fibers are going to be contractible up to some up to some nice choices, whatever this construction of such a fiber bundle corresponds to choosing a family of these Fredholm operators that are parameterized over your base. So our aim now is to construct a virtual vector bundle over, and it should not be T here, but X, I'm sorry. No, not X. It should be over D. So we somehow want to construct a virtual bundle over this, either this big space here or this like already contracted space here, and reinterpret this index here as the virtual rank of this, like that goes from this K0 theory to Z. Okay, so what are going to be the fibers of this virtual vector bundle? So for that, we need to talk a bit more about linear algebra. So, which also should hint to homotopy people why we care about like suspension spectra. So it's the next thing. So if your Fredholm operator is surjective, it means that the co-kernel, right, is just 0, and it means that its index is just its kernel. So the fiber over those surjective Fredholm operators are going to be precisely their kernels. But what happens if D is not surjective? Well, then we kind of stabilize the operator and make it into a surjective operator. What does it mean? So there exists a stabilization T, so that it restricts to X on this direct sum, like N is a finite number, right? I should say that T is surjective, the Fredholm operator, and the index is unchanged. And how to construct such a fella? You just realize that the co-kernel by some a Han-Banach theorem can be represented as a span of these vectors, and then you write the stabilization of rank n of your operator as like just a linear isomorphism of two finite dimensional vector spaces. You add them together, and that's your stabilized operator. And the fiber over D of this virtual vector bundle is going to be such a virtual vector bundle that if you sum it with a trivial vector bundle, you're going to get a kernel of the stabilized operator there. So voila, we have our index bundle. We are gonna denote it with E and F because our family of Fredholm operators went from E to F. Okay, any questions? No, okay, good. So we are short on time. So let me explain to you what is this nice class of Fredholm operators. So in here, I wrote in a super tiny font, which I now see is a very, that is a very bad choice. I wrote this lower index CR. So we have these Cauchy-Riemann operators that we absolutely adore because they behave fantastically well. So what are those Fredholm operators? So you take your symplectic manifold, you take a domain, which for us is a disk with a boundary, which is a circle, right? As a subset of C with some complex structure. It doesn't have to be necessarily the standard one, but whatever. And you take a bundle pair over your disk. So the bundle pair is very special. First, it has almost complex structure, which means that there is an endomorphism of the bundle which squares to minus in identity. And moreover, the F is somehow totally real. That means that when you choose some metric on E, like this this endomorphism maps your F to something which is like normal or orthogonal to your original space that you started with. Okay, so that is something that we are gonna talk about. And what more are you gonna choose? So you're gonna choose some connections on E. And the fun part is that this connection, it can't be smooth. It's of some Sobolev class. And these somehow connections are nothing else than an affine space where you have a smooth Hermitian connections on your bundle here, and in here it's like a torsor over this set, right? Where this A is somehow anti not anti-complex, that's not the word in English, anti-holomorphic section of some endomorphism real bundle. Whatever, you can kind of ignore this, but this is the reason why your fibers are contractible. So in case you're thinking about that, this is the reason, because all those spaces are affine here. So yeah, that's the reason. Okay, so we will define a real linear Cauchy-Riemann operator of this class where our Q is bigger than 2. Also, Noah writes this and doesn't write in any details. Like you need this weird choice of Q for some regularity theory to work, to be able to use the Ehrlich-Kodranchoff theorem to have some compact embeddings of some Sobolev spaces. And these Cauchy-Riemann operators, they just eat some sections of this bundle pair and spits out some anti-holomorphic or not anti-holomorphic, but complex antilinear form on this bundle E. Okay, and those Cauchy-Riemann operators, they have to satisfy this Leibniz rule. Okay, so what is the motto when you work with such fellas? They are amazing, and the same thing has to be true for their index bundles. So now we are gonna take some bundle pair parametrized over some finite or like some CW complex, which is nice. And there are like things that they satisfy. So they're well-defined up to stable isomorphism. It is, if X is not compact, then we can drain it by compacts and we can take colimits and it appear like it's gonna be fine. If it transforms well under pullbacks, it behaves well under direct sums. It reacts extremely well to stable isomorphisms and to tensoring with a real virtual vector bundle, where I write isomorphic with S if it's a stable isomorphism. Okay, so now I have last 8 minutes to talk about stuff. So let me say the following thing. So these index bundles of Cauchy-Riemann operators are so nice that we can actually compute their virtual rank, and that we can compute from a Riemann-Roch theorem. So there you see that the virtual rank is n plus some number, and this number is called the Maslov index, and it somehow records how your totally real bundle twists along your boundary of your domain. So this is somehow the geometric intuition, but the proper math statement should be that it is the image of f under this map of under this map, because you can somehow see the totally real spaces as elements in here. Okay, so how this relates to our orientations. So this should be set. So what is an R orientation? So just let me recall it. It's written in the super small font here at the top. So if you don't remember, if you have a vector bundle and you take its Thom space, if there is a morphism from its Thom space to the n suspension, when n is the rank of your vector bundle of some ring spectrum R, that's called the Thom class, and it is called the Thom class if it restricts on fibers to plus or minus the units of the ring spectrum that you work with. So that's an R orientation, and you have such a thing. You can also do it for virtual bundles, but there is like zero time to talk about everything. But it works fine. It works as you would like it to work. So this our orientation on this index bundle is a choice of orientation with respect to all the CW complexes, which is somehow compatible with restrictions. Yeah, so this is quite weird, but anyways, this choice kind of exists for sometimes for some R. So this index bundle indeed can be R orientable or yeah, is R oriented or R orientable, and how hard it is to orient it. So if you have a stable trivialization of your bundle pair, then it actually induces a stable trivialization of this index bundle E and F, and that gives you like this is like kind of obvious in a homotopy theory that if you already have something that is stable trivializable, then you get this orientation for completely any ring spectrum, and it is super nice because it is compatible with these direct sums and pullbacks. Also, a good thing to know is that if you have stable trivialization of this totally real subbundle, that induces a stable complex structure on this index bundle, and that is also compatible with these natural operations. So that's somehow a reason for, like, from a homotopy theory point, that as soon as you can stably trivialize this fella here, you can stably trivialize this index bundle, and you can get this orientation all the time. Like, it doesn't matter what ring spectrum you choose. Okay, so this was super quick. So now we have we have an option. I have 3 minutes. Either I will tell you for these choices at the start for different extraordinary homological theories, or like for different ring spectra, what you have to do to orient your moduli spaces, but it will take me at least another 20 to 30 minutes to go over all of them, because that's impossible to do in detail in 3 minutes, or I will just stop and you can ask questions. I don't know, make your choice. Okay, no one seems to have an opinion.
Maybe it's a good time to call it. Can you say just very quickly? So that's my question. Like, how do we? Now you have these orientations of these index bundles, but how does that translate to? What's the precise relationship to the bundle that you have in this W, the cobordism?
That's a good question. I didn't write it down. I should have. So this how is this fella here related to the index bundle? So the tangent space of this manifold W is nothing else than the index bundle plus R of your Cauchy-Riemann operator. So that's how it is related. You have to prove it. It takes but it's somehow obvious from the constructions, but you have to read through all the constructions for it to be obvious. So yeah, so the tangent space of W is the index bundle of the family, of the parametrized family of your Cauchy-Riemann operators over the disk, and plus R, which is this L dimension that you're taking, because you had to, where is it? You had to somehow wiggle the almost complex structure. But the wiggling in the almost complex structure, it's like, it basically does nothing. So it just makes everything work. But like from a structural point of view, it is this trivial direction that you just don't need. And then this orientation on this index bundle in the of W then restricts well to our orientation of the ends, that you also have to prove that your construction is not ruining this. Yeah. And that's also the reason why you have this map pi here. Yeah, okay.
Good.
Thanks for the question.
Okay, so if that's all, then I think we'll thank Filip. It was a great talk. And if you can stop the recording, Ade, we can take some more questions.